This is your presenter Asloob Mudassar, and I am presenting slide number 60 of the course on laser physics. Question is, discuss gain saturation for homogeneous line absorption for the case of a 4-level laser system. The answer is, a 4-level laser system with possible transitions is shown in figure 1. So let's see this figure first. So these are the 4 levels of a 4-level laser system labeled as 1, 2, 3 and 4. Let's read the caption. Energy levels and transitions in gain saturation in a 4-level laser system. Pumping is shown from level 1 to level number 4. The pumping rate is represented by Rp and is given by Wp multiplied by N1, because N1 is the population of level 1 at any time t, and Wp is the pumping transition rate, and Rp is actually the total pumping rate of the system. From level 1 to level number 4. Level number 4 is a fast decaying level, so no population will gather in the level 4. All the population that appears in level 4 will immediately decay to level number 3. So level number 4 practically will remain empty. From the level number 3, the population will compile over here. So this will act as the upper lasing level, and the population decay from level number 3 to level number 2 will result in a lasing process. The level 2 is again a fast emptying level, is a fast decaying level. So the population at level 2 at any time will almost be 0. So the level 2 will nearly be empty, and the population inversion is achieved between level 3 and level 2. So that's why we call it lasing levels. So the population decay will be accompanied by the processes which is WN3. W is the stimulated emission transition rate, or you can say over here that W is the, in this particular case, which is the downward arrow multiplied by W multiplied by N3, I can say that this is the stimulated emission rate multiplied by the population of level 3, which is N3. So WN3 is the term which is due to stimulated emission, and then the next downward arrow is labeled with N3 divided by tau, which is the spontaneous rate emission. 1 over tau is the spontaneous transition rate, and multiplied by N3 will give you the decay rate of the population 3 through spontaneous emission. So there is an upward level from level number 2 pointing towards level number 3, that is labeled with WN2. So W is here. W is actually the same for this stimulated process, whether absorption or emission. So here we are talking about the absorption. WN2 is the absorption rate for the level number 2 pumping, for the level number 2 taking the population from level number 2 to level number 3, and is designated by the absorption transition rate. So WN2 is actually the absorption transition rate from level 2 to level 3. But since the population of level 2 is nearly 0, so we can disregard this quantity, that is WN2 can be disregarded or can be set safely equal to 0. So level 4 is a fast decaying level, no population will gather in level number 4. Level number 2 is also a fast decaying level, no population will gather in level number 2. And the lasing process or the population inversion will be achieved in level number 3 with respect to level number 2. So the lasing process will occur between level number 3 and level number 2. Okay, now let's go back. A 4-level lasing system with possible transitions is shown in figure 60.1, which I have just explained. Population inversion between levels 3 and 2 is produced by some suitable pumping mechanism. Due to rapid transitions, the populations of level 2 and level 4 is assumed to be 0, that is at any time N2 is equal to N4 is equal to 0. That is N2 is equal to 0, N4 is equal to 0. Because these two levels are the fast decaying levels. Thus Wn2 can be set equal to 0. This Wn2 is what we call the stimulated absorption. So we have rejected this term also because N2 is nearly 0. The stimulated emission process represented by Wn3 is dominant over the spontaneous emission process represented by N3 over tau. The rate equation for the population of level 3 can be written as dN3 over dt, that is the rate of decay of level of the population in level number 3 will be equal to Rp, that is the pumping rate, minus W times N3, which is the stimulated emission rate, and minus N3 over tau is actually the emission, is actually the term due to spontaneous emission. So due to these negative signs, the population of level N3 will decrease due to stimulated emission and due to spontaneous emission. But there is a positive sign with the Rp. It means that the pumping will increase the population of level 3. Where Rp is the pumping rate, in the steady state condition, we can say that dN3 over dt is equal to 0. That is, the population is no more changing with the time. That is the condition of steady state. So under that condition, if you put dN3 over dt is equal to 0 in equation number 60.1, you will get N3 is equal to Rp multiplied by tau divided by 1 plus W into tau. And this is equation number 60.2. So you can get the value of N3 from this equation. But W is equal to, that is the stimulated transition rate, whether stimulated absorption rate or stimulated emission rate, both are equal in this case, and W is equal to sigma into I over H nu. You see that sigma is the cross section. You can say it a absorption cross section or emission cross section depending upon its definition, and it depends upon the material properties. So we have W is equal to sigma I over H nu. I is the beam which is used for the stimulated emission. You can call it an saturating beam. So I is the saturating beam, H nu is the energy of a photon in the saturating beam. So from here we can solve for I, and I is equal to W into H nu over sigma as given in equation number 60.3. From equation 58.7, saturation intensity for a 4-level system can be written as Is is equal to H nu over sigma into tau. So this is the saturation intensity obtained from equation number 58.7 for the case of a 4-level system. So this Is is actually the twice the saturation intensity for a 2-level system. Thus I over Is, if you take the ratio of these two equations, that is I from equation number 60.3 and Is from equation number 60.4, if you compute the ratio, that is I over Is, that will be equal to W into tau, and equation number 60.2 takes the following form. This equation 60.2 can be written now as replacing W tau by I over Is. So you can see that N3 is equal to N30 divided by 1 plus I over Is as shown in equation number 5. What is the N30? Where N30 is equal to Rp into tau is the population of level 3 in the absence of saturating beam I is equal to 0. So if you set in this equation, that is in equation number 5, if you set I is equal to 0, you will get N30 is equal to N30 is equal to N3. And you see that N3 is actually the N30 can be written also as Rp into tau. That is, which is the population of level 3 in the absence of saturating beam. We can also write from this analysis, that is the equation number 4 we have written, that is the saturating beam for the 4-level system. So for that we can write that the saturation intensity for a 4-level system is equal to twice the saturation intensity for a 2-level system. What is the reason for that? For a 4-level system, the saturation intensity is twice that of a 2-level system. The reason is that this is because in a 2-level system, stimulated emission and stimulated absorption occur between the same 2 levels, and a change in population of one level causes an equal and opposite change of a population in the other level. This makes the saturation intensity of a 2-level system equal to half the saturation intensity of a 4-level system. Now one more thing. Look at tau. We are using tau with Rp, and this tau is the same as we have written for the spontaneous emission term, which is n3 over tau. So tau is actually the lifetime of level number 3 due to spontaneous emission. And for the pumping we need to choose at least tau. For the pumping rate, that is Rp multiplied by tau will give you n30, because you see that n30 will compile over in the level 3, because the population of level 4 will decay immediately to level 3. So the population of level 4 is almost 0, and it means that the pumping that is done is effectively we are pumping the population of level number 3. And you know that in the level number 3 we are using tau 1 over tau as the spontaneous rate. So we are using the same time for at least for the pumping mechanism. So n30 can be written as Rp into tau. But you see that a different tau which may be represented as tau p can be chosen over here. But this tau p must be such that the population of n3 is always available for the lasing process. Consider the idealized experiment of equation number 53, where we used the probe beam of variable frequency nu prime and the intensity I prime of nu prime in order to measure the gain, that is given by a gain is equal to sigma into n3 minus n2. So this is actually the gain coefficient, and sigma may be called over here actually the emission coefficient, emission cross section, because we are using level from level number 3 to level number 2. So this will give you the gain of the system. But if we are using n2 minus n3 over here, then this g will be replaced by alpha, which will be the absorption coefficient. But here since we are want to calculate the gain coefficient, we have written g is equal to sigma times n3 minus n2. And we are using the same sigma both for n3 and for n2. Though these could be different, that is sigma could be different for level 2, sigma could be different for level 3. But we are using the same value of sigma because we know that the population of n2 will be equal to 0. But if the population of n2 is not 0, we could use different sigma for n2 level, because sigma depends upon the properties of the material. And for material, the n2 value for sigma could be different for the n3 value. But since we are setting n2 is equal to nearly 0, so we are using the same sigma over here. So g is equal to sigma times n3 minus n2 is the gain coefficient of the system rather than the absorption, because for the absorption we shall represent g by alpha, and instead we shall write, instead of n3 minus n2 we shall write n2 minus n3. But since we are talking about the gain coefficient, we are writing g is equal to sigma multiplied by n3 minus n2 instead of the absorption, which for the present case we can set n2 approximately equal to 0, and n3 given by equation number 60.1 takes the following form. So n3 from equation number this can be written in terms of the g value. So we can write g is equal to sigma, putting the value of n3 over here from equation number 5 and setting n2 is equal to 0, we have g is equal to sigma times n30 divided by 1 plus I over is. and sigma multiplied by N30 can be combined into a single term, which is G naught. So G is equal to G naught over 1 plus I over IS. This G naught is equal to sigma times N30 is the gain coefficient for I is equal to 0. Because if you put I is equal to 0 over here, you will get G naught is equal to G. So that's why we have called this as a gain coefficient for I is equal to 0. That is in the absence of saturating beam and may be regarded as unsaturated gain coefficient. So G naught may be regarded as unsaturated gain coefficient because it is defined in when the saturating beam, when the intensity I of the saturating beam is 0, using sigma for homogeneous broadening. So sigma for the case of the homogeneous broadening, following equation number 40.2 can be written as, so the unsaturated gain coefficient is given by G naught is equal to, you see that G naught is actually this quantity, G naught is equal to alpha times N30. So here we are putting the value of sigma from equation number 40.2. So we have G naught is equal to 2 pi square over 3 N epsilon naught CH multiplied in the numerator by the absolute square of mu multiplied by N30 multiplied by nu prime and multiplied by G of nu prime minus nu naught, where nu prime is the variable frequency of the probe beam. So you see that we have found G naught. From equation number 60.6, that is from this equation, it follows that G will decrease as I increases, as obvious over here. G will decrease when I will increase. That is when the intensity of the saturating beam will increase, the gain coefficient will decrease, while the gain profile will remain unchanged. So gain profile, the shape of the gain profile will not change because it is determined by G of nu prime minus nu. Since this gain profile would not change when we plug in the value of, when we set the value of saturating beam, either we increase the intensity of the saturating beam or decrease, the gain profile will stay the same. That is, the profile will stay the same. However, the value of the profile at the frequency nu naught, that is at the resonating frequency, will be different. So this is what we have explained. All the parameters, all the aspects of the questions have been addressed. So this is the end of slide number 60.